So, how do we measure total carbohydrate? April?
You take the total 100 and subtract the moisture and protein.
Yes, so if I want to measure total carbohydrate in a sample for labeling, I would take 100 and subtract everything, all of the other approximate values. But if I have a carbohydrate solution, or if I have a sample with simple carbohydrate, no other matrices in there, what was the method that I used or would use next week in the lab to determine total carbohydrate? Yeah, look through the notes, that's okay. What was it? What was the method? This is what you're going to be doing next week. Thea? Phenol sulfuric acid method. So in that method, you break down the glycosidic bonds by H2SO4, and then we have your monomers in the presence of concentrated acid, and the heat generated from having the acid will form furans. Furans will react with phenol and give you a colored compound that you would measure spectrophotometrically. And then you use a standard to plot a standard curve and then determine the amount of carbohydrate in your sample. And that's basically what you'll be doing next week. What are the preparatory steps for carbohydrate analysis? So if you have a complex matrix, and let's say you want to determine carbohydrates, simple sugars. Let's go with simple sugars. What would be your first thing to do? You have a sample that is higher than 10% moisture. You have to extract the moisture and let it dry. So you dry it out. So you dry your sample to remove the moisture. That's one thing. What if you have fat in there? You extract the fat. You remove the fat either by batch extraction with an organic solvent or toxin extraction. And then now, at that point, you have your carbohydrate. Yes?
Is there a certain percentage that can be under it that you don't have to pre-dry?
Yeah, well, usually under 10%, you just leave it as is. So we said, but if I ask you this question, what would be preparatory steps? The first thing you want to say is you want to have a homogeneous representative sample. So you want to have a representative sample from your lot. Then you would remove the moisture and defat. So you want to say select a representative and homogeneous sample. Okay. So dehydrate, defat, and then how do we extract from this mixture the monodi and oligosaccharides? So now you have removed the moisture, removed the fat. How would you separate the monodi oligosaccharides from polysaccharides and protein? Not one of you remember what we covered on Monday. Why would we? It's just boring material. Except Laura.
Is that where we learn the ion exchange?
That's one of the methods. That's one of the methods to determine. Oh.
To be able, because then you get the protein value of the charge and then you end up with.
Okay, so there is ion exchange cleaning, but before that, there's one important step before that. Will, you solubilize in 80% ethanol and, with heat. So you would use 80% methanol and heat it up, ethanol. And that alcohol is going to solubilize your small sugars, whereas your polysaccharides and your protein will precipitate. So at this point, you have a solution of 80% ethanol with your sugars that might have, Laura, those amino acids that are charged in organic acids and salts. Then you clean them up with the ionic resin. Then you clean those charged molecules out, and then you would have your monodi and oligosaccharides. So what are some categories of methods for determining monodi and oligosaccharides? So now you have your monodi and oligosaccharides. What three categories we talked about? Yeah. Calorimetric methods, yes, based on the reducing power of these monodi and oligosaccharides. That's one. Another one, April? Enzymatic. And the last one that we started off page? Chromatography. Okay, and that's where we left off. So, before we go to where we left off, what is the basis of carbohydrate analysis using enzymes? So when we use enzymes, the enzymes are reacting with your carbohydrates as substrates. So the enzymes uses these carbohydrates as substrates, convert them to product. Sometimes the product can be measured by spectrophotometry. Sometimes we need another reaction to generate a product that will be able to absorb light. So that's why sometimes we have the dual enzymatic reactions. Okay. So we were talking last about normal phase, and we said in normal phase the interaction is via hydrogen bonding with an amine modified silica, where your sugars will react via hydrogen bonds, and those that have more hydroxyl groups will react more with the column. So therefore monosaccharides will come out first, then disaccharides and trisaccharides and bigger molecules. So hence the order that you see here. We have disadvantages with the amine bonded stationary phase, because with amine groups, some of the reducing sugars might react with the amine group reducing shift phase, and basically bleach off or cut off your amine groups from your column. So that means you lose efficiency of the column, you lose selectivity of the column by just stripping off the amine groups. In order to solve this problem, you can regenerate the column. You can regenerate by adding modifiers to your mobile phase. In the mobile phase, that means you add amine groups that will replenish your supply of amine groups on the silica. Then you can run your samples again. So that means you have to continuously regenerate your column because you lose amine groups due to reaction with reducing ends. Other modified silica that can be used for normal phase are diol bonded and cyano bonded. These are two other types of stationary phases that can be used as well as modified silica phases for normal phase HPLC. Okay, so you can also use reverse phase HPLC. Reverse phase, can you please tell me what the stationary phase would be? Well, it's right there. Reverse phase, 18, C18 columns. So is that polar or non-polar? Non-polar. So your stationary phase is non-polar and your mobile phase is polar. So it says here separation of monosaccharides is difficult. Why do you think it's difficult? Think about the chemistry of your sugars. Why is it difficult to separate them using reverse phase? Remember the most important principle of chromatography. What's the first step in chromatography that you need to happen? Separation to occur. Well, interact with the stationary phase. Very good. So if I have a non-polar stationary phase and a polar mobile phase, where do you think the sugars will be? The monomers. Will they want to interact with the column? No. So you will barely have any separation between the monomers. They might just want to elute, go out with your polar phase without separation. So one way to solve this problem is adding salt to your mobile phase. If you add salt to the mobile phase, you're basically making the mobile phase, the water in the mobile phase, not very available for the sugars because of the presence of salt. Then the sugars will interact with your stationary phase and essentially separate. Another problem is the formation of anomers. So you have in your samples, you have anomers in these different locations, alpha versus beta location of your hydroxyl group here. So these could be present in your solution at any time point. This will result in a double peak. So you will, instead of having one peak of that same compound, you will see a peak that is split because these might interact slightly different with your stationary phase, resulting in a split-like peak. So to prevent that split-like peak, which makes it really hard for integration, you can induce the anomerization. That means you can drive them all to be in one form. So you can add amine groups to the mobile phase, so that will force all of them to be in one form, which is the beta form. This way you will have one peak that is not split. Yeah.
Could you please say that again? Explain this to
Okay. So if I have anomers, instead of having one peak of my compound, if I have anomers that they continuously exchange between alpha and beta, then when they interact with the column, they interact slightly different, so you end up with a peak that is split. So it's really hard to integrate this kind of peak. So to prevent that and make sure that we have only one peak that we're integrating, so we force them all to be in one form. We force them all to be in the beta form anomer. So in this case, you just force the anomerization by using amine groups. Amine groups will force the anomerization into one form, and therefore you will end up having one peak. Okay. You can do anion exchange chromatography as well. In nature, sugars are not ionized, right? So they don't carry a charge. But they are very, very, very mild acids. That means they will give their protons. So the hydroxyl groups in the sugar will give out its hydrogen only at really high pH. At very high pH, they can get ionized. That means they can give you their proton and become negatively charged. Because we say that sugars are very, very weak acids. So at really high pH, alkaline pH, you can drive them to be negatively charged. So once they're negatively charged, then you can use anion exchange chromatography. So the anion exchange, meaning we are exchanging the anions. The anions, or the negatively charged molecules, can go between the stationary phase and the mobile phase. So we use polystyrene, divinylbenzene, and copolymers that are derivatized to carry a positive charge. And then they will interact with the negatively charged sugar. And because they carry charge, we can use pulsed amperometric detection, PAD, or what we also formally call as pulsed electrochemical detector. That would be a common detector that could be used for this type of chromatography. What would be the order of elution in this case? If you have glucose and sucrose, which would come first, glucose or sucrose? The compound that interact the most with the column will come later. which will interact more with the column, glucose or sucrose under high alkaline pH? Sucrose, because you have more OH groups. So the potential of ionization is more. So when the potential of ionization is more, that means it will interact more with the column. So these are examples of sugars in molasses: glucose, fructose, and sucrose. And then here, lactose is an internal standard because you don't have lactose in molasses. So that would be the order of elution. Last chromatographic method is cation exchange. So can we make them positively charged? Can we make the sugars positively charged? Is there any way you can make those sugars positively charged? Not really. No. You cannot ionize them. So because you cannot make them positively charged, in order to separate them based on cation exchange chromatography, you have to do two things. First, have counter ions, either calcium or silver. So with that, the positive charge are going to interact with the hydroxyl groups of your sugars. So we call this interaction forming coordination complexes. So you're going to form a coordination complex with a positively charged ion. So then this positively charged ion that is interacting with this molecule will then interact with your negatively charged column. But there is another mode of separation that is size exclusion. So there is a combination, you're separating based on size and charge. And in size exclusion, the larger molecule comes out first, and the smallest molecule comes out last. So the order of elution here is swap. So you can see that sucrose comes out first, then glucose, then fructose, which fructose is the smallest in coordination. Okay, it's a pentose, not a hexose. Okay. So you can use counter ions like calcium, for example, or you can use dilute acids where protons, the hydrogen ion, is the one that is forming coordination complex. Okay. All right, this is the last one for HPLC, but we can also do GC for neutral mono and di oligosaccharides. So we can actually use GC to measure these sugars. However, there's a problem. Are they volatile? Are the sugars volatile? They're not volatile. They're not thermally stable. So what do? We have to derivatize them. Okay? So we have to make them, change them into compounds that are volatile and thermally stable. So you can derivatize these sugars by different chemical reactions. You can do acidification with silane groups, so silylation, or acetylation, or trifluoroacetylation. So different ones have different characteristics. So the silated derivatives are more volatile. The silation also suitable for disaccharides, but acetylation is suitable for monosaccharides. So if you have monosaccharides that you want to determine, you can do acetylation, but first you have to reduce the sugars into sugar alcohol with sodium borohydride. Sodium borohydride, convert them to sugar alcohols, and from there you acetylate with acetic anhydride to generate an acetylated or acetyl ester. And then this is volatile and thermally stable, so you can use your regular GC, specific column, FID, for circulation and determination. In this example, it's mannose, glucose, galactose. Okay, so great. Moving on to starch. So starch and dietary fiber. So for starch, we often determine total starch. And sometimes you want to determine degree of gelatinization of starch and degree of retrogradation. So you want to check, for example, if you're processing and you want to determine the impact of processing or storage, the impact of processing on starch gelatinization, the impact of processing on retrogradation, like in the formation of pasta, or the impact of storage on starch retrogradation. So if you're studying that, you need to be able to determine these parameters. Okay. And then there is the dietary fiber, where you can determine pectin if you have a food product that mainly composed of pectin, like jellies and jello and jams. Or if you want to determine total dietary fiber in different food products, and especially for food labeling, for nutrition labeling, you need the total dietary fiber measurement. Okay. So with total starch, there is qualitative analysis where you determine whether or not starch is present. And this is simple. Starch and iodine form a blue complex. You can put a drop of iodine in your sample, and if there's starch, it will turn blue. If you don't have starch, it won't turn color. Microscopy is often used to look at the difference in starch granules among different samples. So this is kind of qualitative analysis of starch. But what we care for here is quantitative analysis, and total starch is based on enzymatic methods of analysis. So you have total starch. So in order to get the total amount of starch, we have to break down the starch into the monomeric form, which is the glucose, the building block of starch. So how do we break down starch into glucose? Without looking further into your slides, remember from your food chemistry, how would you break, what enzymes would you use to convert starch to glucose? Zach? Yes, that would be amylase. So I'll show you the chart that you should have seen in food chemistry. This shows you the different enzymes that act on starch. And we will be talking about all these enzymes for different assays. Okay? First, you have your alpha amylase, which is very important enzyme. It's an endoenzyme. The alpha amylase is going to chop inside of the starch, anywhere internally in the starch molecule. So it would go inside and chop it. So you end up with maltodextrin, basically. So shorter branches or shorter chains of glucose. So that's an endoenzyme. Another endoenzyme is polymerase, which is a debranching enzyme. So it's going to cut off your glucosidic linkages that are alpha-1,6. So the alpha-1,6 bond linkage is going to be broken by polymerase. The alpha amylase can also debranch as well, but it mostly cuts the alpha-1,4 linkages. Okay, so these are your enzymes. Now, what's important in starch analysis is also using glucoamylase. Glucoamylase is very important because it's an exoenzyme, and it chops one glucose unit at a time. So your endoamylase, alpha amylase, is going to break it down into smaller chunks, smaller chains, and then the glucoamylase is going to come in and chop one at a time to give you that glucose, all of them into glucose units. Okay? The last one here that will come in handy later on when we measure starch gelatinization is beta amylase. Beta amylase, it cleaves mostly 2 glucose units at a time. So it gives you maltose. So 2 glucose units are maltose. So it cleaves 2 glucose units, and sometimes it might cleave at 1, 2, 3. So you might get maltose or triglucose. But this is an exo, so now we have 2 exoenzymes, glucoamylase, beta amylase. We have 2 endoenzymes, alpha amylase and choline. So for starch determination, so the kit that we usually buy to determine total starch would have mainly alpha amylase and glucoamylase. So in our kit, the alpha amylase will chop up the starch into smaller branches or smaller chains, and then the glucoamylase will cleave up 1 glucose unit at a time, so you end up with all glucose. So you end up with glucose. Now I need the enzymatic reaction that will give me color change so that I can measure my constituents or my substrate. So here we can often see that the kit, the Megazyme kit that we usually purchase, also comes with this, with these enzymes, glucose oxidase and peroxidase. So what happens with the glucose oxidase, so these are coupled reactions. So with the first reaction, which is the measuring reaction, glucose oxidase in presence of oxygen, you get peroxide and you get gluconolactone. We don't care about the gluconolactone. This product here we don't care for. What we care for is for this peroxide here that is generated. So then the second reaction, which is the indicator reaction, the peroxide in the presence of a reduced dye. So the peroxide will oxidize the dye, give you an oxidized dye that has a color. That's what you measure, but we need peroxidase to initiate this reaction. Okay? So now these are the coupled enzymatic reaction that would give us a measurement. We will calculate total glucose and convert that to the amount of total sugar, total starch. Okay. So, if you remember last time we asked, do we use the same method to measure degree of gelatinization and degree of retrogradation? The answer is yes. So the same method is used to measure, to determine either degree of gelatinization or degree of retrogradation. How does that work? Okay. So if you think of starch, raw starch and retrogradated starch are not digested by beta amylase and pollinase. Okay? So raw starch and retrogradated starch cannot be digested by pollinase and beta amylase. Pollinase debranching enzyme. Beta amylase is the enzyme that cuts 2 at a time or 3 at a time. So maltoses or maltotrioses. Okay. So if I am processing and want to determine how much of my starch got gelatinized, I can use pollinase enzyme and alpha amylase. They will both work on a gelatinized starch. So a gelatinized starch will be hydrolyzed by these. So this is going to debranch first, and then beta amylase is going to cleave into maltoses and maltotrioses, which are reducing sugars. Then I can measure the amount of reducing sugar following any of the methods we talked about last time. The most common one is Smoogie-Nelson. Yes?
So can amylase only hydrolyze gelatinized starch?
Beta amylase. Alpha amylase would prefer, is more active with gelatinized starch, but can also hydrolyze a raw starch. But beta amylase, you have to have the starch in the gelatinized form for it to act. Okay. And if we look at degree of retrogradation, if we're following starch retrogradation over storage, for example, then what we will see is a reduction in the amount of reducing sugars that can be produced. Why? Because retrograded starch will not be hydrolyzed by pollinase and beta amylase. So less reducing sugar will be produced. Okay? So over time, if I'm looking at degree of retrogradation over time, so we are starting at time 0, let's say all of our starch is gelatinized, I have my maximum reducing power, then over time I can see reduction in my reducing power because the enzyme will no longer be able to hydrolyze the retrogradated starch. Okay, is that clear? Okay. All right, moving along. Dietary fiber. So the dietary fiber, we defined it as this plant material that is not digested or absorbed in the human small intestine, and it can be fermented either partially or completely in the large intestine by microorganisms. Okay, so dietary fiber can include polysaccharides, oligosaccharides, oligofructans, that means saccharide that made up of fructose chain, or lignin. Lignin is not a carbohydrate. Okay, so we have two categories. We have the soluble fiber made up of pectin and hydrocolloids. High in beans, oat bran, fruits, and vegetables, we have soluble fiber. Insoluble fiber, these are the fibers that are mainly in the cell wall material, celluloses. Hemicelluloses can be, some of them are soluble, some of them are insoluble, but mostly insoluble. Lignin and resistant starch is also insoluble and it's non-digestible, so that's why it falls under insoluble fiber. Because of these different components that differ in characteristics, it's very hard to analyze all of these different components in a single approach. So there we have different approaches and sometimes a very lengthy procedure to be able to identify and determine the quantities of each component. Okay. Rachel can speak to the lengthy procedure. Right? Okay. So, in the past, dietary fiber was measured via a crude method, which is no longer acceptable for food. You won't find it in your chapter in the book anymore. They removed it from the book chapter because it's not used anymore for food. But I like to keep it for comparison that originally fiber was determined using the crude method, and in that crude method, what you're measuring is mostly cellulose and lignin and some hemicellulose. You do not measure soluble fiber, and that's why it was removed for human use, but it's still used for animal feed. So for animal feed, you can use these methods to determine crude fiber, but not for human food. So we no longer have the unit. I remember it was here at some point 12 years ago, and then I don't see it anymore, the equipment used for crude fiber. But what it is basically a hot plate, and then you put your sample in a container, and you hook a container to a reflux system. So what it does is you put either acid or alkaline or acidic detergent, a detergent with acid, and then you heat it up and then you reflux for a couple of hours. That means the acid and the detergent is going to break down your proteins and starches and fats, if there is still fat, if you did not defat. And what happens is everything becomes soluble, right? So you break down most of your protein and starches, but what remains is your dietary or your fiber, cellulose, hemicellulose, and lignin. So these will not be solubilized, and you can filter them and then dry them and quantitate them. So, but again, this is crude because it's missing the soluble fiber component. So we don't do that, like I said, anymore for food, human food. What we do is the dietary fiber method, which is an AOAC method, and there's also a ACC method to determine total fiber. So with that, what you do is, first of all, you remove the moisture, you remove the fat, and then you end up with a defatted, dehydrated sample. You first digest the starch, but first you heat up to gelatinize the starch to ensure complete digestion of the starch, and then you adjust pH and digest with a proteinase to break down the protein, and then you add glucoamylase to make sure that all of your maltodextrins and dextrins are converted to glucose. So now you have everything that is soluble. The sugars are soluble, the proteins are soluble. If you take it at this point and you add ethanol, you precipitate the soluble fiber. So already your non-soluble fiber will not be soluble. But when you add ethanol, you are precipitating the soluble fiber. So now all of your fiber is a precipitate. So you filter, you wash your filter with water and ethanol, then you dry it out, and then you correct for protein and ash. If you have anything that is still in your residue as protein and ash, you subtract them from the weight of your total fiber and you get total dietary fiber. So in one step here, you get total dietary fiber that includes soluble and insoluble. Now, if I want to determine soluble fiber and insoluble fiber separately, instead of adding ethanol at this step, I would filter and wash. So in this case, I did not precipitate my soluble fiber. I just separated my insoluble from the soluble. This way I can determine how much insoluble fiber I have versus soluble fiber. So I take the residue, which is the insoluble fiber, that would not be solubilized, obviously. I filter that. I wash with water and ethanol and acetone to wash any residual solubles. I dry, weigh it, and then measure ash and protein in that mass that I've obtained. Again, to correct for any residual protein and ash in my sample. Then I subtract the amount of residual protein and ash from the whatever mass I obtain, and I get the insoluble fiber. So, now the other portion would be my filtrate. In my filtrate, I have my soluble fiber, I have the solubilized proteins and sugars, so I have all of my soluble components. I just want the soluble fiber, so from there, I can take that filtrate and then precipitate it with ethanol. So at this point, I add ethanol to that filtrate. Then I still have my soluble, and then the soluble fiber becomes a precipitate. I filter that, wash it, dry it, correct for protein and ash, and I get my soluble fiber. At this point, I have soluble fiber amount, I have the insoluble fiber amount. If I add them together, I will get my total soluble fiber, total dietary fiber. So there is another method, the English Cumming method, that is based on GC detection mostly. So here, again, the same thing. You get rid of your starch and protein. You take the non-starch polysaccharides at this point, and you hydrolyze by sulfuric acid to get monosaccharides. The reason we do that is not necessarily to quantitate total soluble fiber. It is mostly to look at the composition of my total dietary fiber. What is my total dietary fiber made up of? What is the percentage of cellulose? What's the percentage of lignin? What's the percentage of hemicellulose or pectin or what have you? So this to look at the profile of the different components within the dietary fiber. So when I look at the neutral sugars or the sugars that make up those dietary fiber, I can deduce what different components are within my total dietary fiber. So when I get my monosaccharides after breaking them with sulfuric acid, I can derivatize them and then I can measure them by GCFID. If I have pectin in there, pectin is a polymer of galactouronic acid, which cannot be derivatized, but I can measure uronic acid by colorimetric detection. Uronic acids, actually, the galactouronic acid glycosidic bonds are not broken by the sulfuric acid. So that's why we cannot derivatize them and measure them by GC. Okay, so if I have foods that are mainly composed of sugars and water and pectins, and I want to determine the amount of pectin in there, the way I do that is, first of all, I solubilize and precipitate my pectin, and then from there I can saccharify by NOH, so I can break the esteric bonds in my galactouronic acid, so this the methoxy groups here, and then after that I would have negative charges that can be precipitated by calcium ions to form calcium lactate. So these are precipitated and measured gravimetrically, so by weighing them. Okay, so what we want you to do is homework for +5. So it is not required, but if you do it, you get a bonus +5. It will help you understand how the method is done in terms of calculation, since we're not doing that in the lab. So what you have here is after we filter, we have the residual that are filtered out, and then the soluble part that we precipitate with ethanol separately also are filtered into a crucible. So in a crucible, I would have the residue after I filtered all of the soluble parts or the filtrates. So this would be the weight of my crucible, rep 1, rep 2, rep 1, rep 2. And then I weigh it after I filter everything and I dry it, so everything is in the crucible, is my fiber. Here's the insoluble and here's the soluble. Usually I take one of my reps to measure protein content, and because the method is destructive, it's no longer part of my replication. It's used up to determine the protein content. And then also, I take the residue from the other crucible and I ash it to determine the ash content. So the protein and ash are done in a single rep. Okay, so I have 2 reps to start with. 1 rep is used for protein determination, and 1 rep is used for ash determination. Okay? So I'm measuring protein in each and ash content in each. I run a blank alongside where I do the same thing without any sample, and I measure the fiber in the blank sample, the protein in the blank, and the ash in the blank. So you have all of these values. And then this is the initial weight of the sample, rep 1, rep 2. So now what you need to do with all of this given is calculate percent total, insoluble, and soluble fiber. So these are the things that you need to look for. What's the average sample weight? Then you get the insoluble residue 1 and 2. Get the average sample for the blank and for the sample, average value for the sample and for the blank. And then you subtract the value of the blank from the value of the samples. And then you have all of these procedures that you have to follow. You do that for the insoluble and repeat for the soluble, and then the value of the soluble fiber you add to the value of the insoluble, and you get the total fiber content. So you work on that, and then next Monday you can bring it in for a +5. Once you turn it in, I will post online the key so that all of you know how to actually calculate. Okay? That is all.